Lithium-ion batteries have become the ideal power source for cell phones, laptops, and electric vehicles. The estimated demand for lithium in 2030 is 5 times the current size of available lithium supplies. Conventional lithium mining currently involves extracting from hard rocks and salt flats, with most mining activities concentrated in the lithium triangle of Chile, Argentina, and Bolivia. The United States urgently needs to develop a domestic lithium supply to ensure energy security. Unconventional resources, such as the Salton Sea geothermal brine, have the potential to serve as a domestic lithium source. Conventional methods for lithium extraction require large evaporation ponds and significant chemical inputs. In comparison, Ellexco's electrochemical technologies take advantage of electricity as the sole input, without the use of evaporation ponds or chemicals, and generate no waste. Our team is located in the national capital, Washington, D.C., and supported by the research resources of George Washington University and the University of Chicago. Our core team members are Professor Shitang Liu and Lingchen Kong from George Washington University and Professor Chang Liu from University of Chicago. Active lithium intercalation material powder was first well mixed with binder and suspended into solvent as an electrode slurry, and then we casted the slurry on a porous carbon substrate to fabricate the final electrode. The lithium intercalation electrode was assembled into the extraction cell as the working electrode. The anion exchange membrane and activated carbon electrode were assembled on the counter electrode side. Salton Sea geothermal brine was fed into the extraction cell with a continuous flow. Extraction of lithium began when we applied a negative constant current. After extraction, we switched the feeding solution to the release solution and collected lithium chloride solution by applying a constant positive current. The lithium selectivity was determined by measuring cation concentration in the release solution by inductively coupled plasma optical emission spectroscopy. By feeding in the complex synthetic geothermal brine containing lithium, sodium, calcium, and potassium, as well as iron, manganese, boron, and strontium, lithium only takes around 0.7% in the influent and takes over 91% in the effluent. The lithium chloride solution was then fed into bipolar membrane electrodialysis cell to produce lithium hydroxide. Electrolysis occurs on the bipolar membranes. Lithium migrates through the cation exchange membrane and forms lithium hydroxide. After measuring the species concentrations in the dilute in channel, we found the concentration increase over time. Lithium hydroxide was gradually generated in the channel, and the chloride ion concentration is always negligible. The average purity of lithium hydroxide is produced at 99.6%, which reaches battery manufacturing grade. Lithium hydroxide solution was then sent for crystallization and finally made into a white powder of lithium hydroxide monohydrate. To maintain the potential stability, we designed concentration stepwise extraction cell series. The brine with partial lithium extraction will go through the extraction cell until the majority of lithium in the brine is extracted. We've conducted techno-economic assessments for our lithium extraction process using intercalation materials. We consider the contribution of both capital and operating costs to the levelized cost of lithium. Based on the lab experimental data and some practical assumptions, the final levelized cost of lithium by our electrochemical process is less than $5,000 per ton, which is lower than conventional mining costs and way lower than battery-grade lithium hydroxide market price. Furthermore, the chemical-free process will promote the electrification of mining industry and lower the environmental impacts caused by mining activities. Our goal is to make lithium extraction cost-effective and environmentally friendly.